Hello everyone, myself Sunita, and today I am going to present about the trading interface time compute for adversarial robustness. And coming to the introduction part, AI models, especially deep neural networks, are widely used in image recognitions and also the natural language processing and more. However, they are vulnerable to advertised attacks. Small intentional permutations added to input data that mislead the model into the making incorrect predictions. And also coming to the motivation, the traditional solution is adversarial training, where the model is trained using adversarial examples. While effective, this approach is extremely resource and also intensive. It requires generating attacks and retraining the model repeatedly. And also coming to the significance of this, it this approach works, it can help organizations and also protect AI systems are more efficiently without the burden of retaining every time a new type of adversarial threat appears. And coming to the next problem statement, here we have adversarial attacks. These are mainly strategic manipulations of input data designed to fool AI models. Even tiny changes invisible to the human eye can lead to the model to make incorrect predictions. And the current limitations, adversarial training is more expensive and many defense techniques degrade the accuracy of model on clean and also the non-adversarial data. And worst of all, most defenses fail against unseen attack methods. Coming to the research questions, more computation at the time of interface, like more processing steps or deeper analysis to make the model more robust without needing adversarial trainings. And also coming to the proposed methods of this slide, it refers to the resource used when a model makes a prediction. By increasing this compute, the model can potentially evaluate the input more thoroughly, making it harder for adversarial inputs to succeed. Coming to the strategy of this, we have dynamically allocate more computational purpose of when the model detects inputs that might be adversarial. This can involve more internal layers being activated or deeper evaluations. And also coming to the model section of this, we have two OpenAI models. Preview Mini, a larger, more complex model is called Preview, and also a lightweight model user for comparisons of this many. This helps evaluate whether the method works across model of different sizes and capabilities. Coming to the experimental setup, here we have two types of attacks. We tested against two main types, that those are white box attacks and also the black box attacks. Here coming to the white box attacks, where the attacker knows the model internals is called white box and the attacker only sees the inputs and outputs is called black box attacks. These represents the realistic threats of the scenarios. Coming to the evaluation metrics, we have attack success rate and computational trade-offs. And attack success rate, how often attacks fool the model, and also how much more latency or power is consumed. Coming to the testing environment of this, here we have a data sets used, that's our MNIST or simple digit classification for this, and also color images of objects, image net subsets, real world high resolution images using varied datasets. And also coming to the baselines, we first evaluated both models without any enhanced compute or adversarial attacks, and then tested again with that increased compute under attack to compare the performance of these changes of these baseline models. Coming to the next Key findings here, the results are, if it comes to the positive of increased interface time, compute significantly reduced attack success rate, and especially effective in detecting and resisting white box attacks. But when the some attacks still bypassed this defense is called, and also latency or delay in getting predictions increased. In other words, while this method boosts security, it comes at a performance cost. Coming to the next, strengthens no need for adversarial returnings. It saves time and resources, and flexible defenses applicable to different types of models, and real-time security. Coming to that, adaptively increases such based on context or suspensions. This makes it very useful for real world deployment, especially in situations and also where the retelling is feasible. And coming to the limitations, despite its promises, there are a few limitations. The first one is computational cost, and second one is not a universal shield, and the last one is trade-off between speed and security. Coming to the cost of the computational cost, this method needs more power and time during predictions. And coming to the not a universal defense, some advanced or adaptive attacks still manage to break through. Coming to the speed security trade-off, in this environment that needs instant responses like self-driving cars, this method might not be ideal. And coming to the future directions of future scope, optimize compute uses, find smart ways to use just the right amount of extra compute, not too much and not too little. Combine with the traditional defenses, use a hybrid approach that includes both adversarial training and also the interface time compute, and scale it up. Apply this idea to larger language and also the model vision systems, or even multiple model AI like ChatGPT and ChatGPT 4 for this. And the broader applications extend or larger models, and this coming to the models and real world uses. And coming to the conclusion part of this basic project, uh, inferences time comprehensive compute is a promising low effort way to increase AI model security. It can reduce attack success rate without retaining, which is a big deal in terms of cost and practically, but we need to address the trade-offs in terms of speed and computational cost before wide scale adoption. And the trade-offs in compute cost and effectiveness must be addressed. And thank you so much for the attention, and thank you. I'm binding this up.